Alright, so today we're going to talk about Mantel's theorem, which is one of the first results in extremal graph theory slash extremal combinatorics. So what does it say? It says G is a graph with n vertices with no triangles. So no triangles. Then G has at most n squared over 4 edges. So right away we can sort of construct a graph with no triangles. And one way we might do that is the complete bipartite graph, which looks something like this. So I got some colored Sharpies. So let's see if I can draw this. So you have one side of your bipartite graph, and another side, and you have your vertices. We gotta make it complete. And this one way to see that there's no triangles is for any 3 vertices. You pick 3 vertices. By the pigeonhole principle, 2 of them have to be on the same side, either the red side or the blue side. And if 2 are in the same side, then they won't have an edge between them, so they can't compose a triangle. And there's floor of n squared over 4 edges in this graph, so we can see that Mantel's bound n squared over 4 is tight. Okay, so now we can start to prove it. So I'll write proof. So say G has m edges. So then let x and y are vertices. And let's say they're adjacent, so xy is an edge. Then for every edge xy, we have that d of x plus d of y is less than or equal to n, where d is the degree of the vertex. Now, one way to see this is since if that's x and this is y, and maybe this is my other vertex v, right? V can be adjacent to at most one of x and y, right? It could be adjacent to x and you won't have a triangle, or it could be adjacent to y and you won't have a triangle, but it can't be adjacent to both. So for example, if the sum of your degree of x and y was n plus 1, then that would be more than the total number of vertices. So that would tell you that there's a vertex that's being counted twice, a vertex that's being counted twice, which means it's being counted both in the degree of x and the degree of y, so it's adjacent to x and y. So you have to have that's less than or equal to n. But another way of saying that is because for every vertex x, there's degree of x many edges that are incident to x. And so we can sum over the edges of d of x plus d of y and say that's less than or equal to the number of edges times n. Or we can sum over the vertices. Since there's d of x many edges, we could just say d of x squared is less than or equal to mn. Okay. So now we know what this sum is. We know what this is. This is so or wait, we don't know what that is. But we can use, so let's try to use the Cauchy-Schwarz inequality. To do something about this sum. So here's something we do know. So we don't know what the sum of the degree of x squared is, but we do know what the sum of the degree of x squared is. The sum of the degrees is twice the number of edges, because like if you have like an edge, it adds 1 to the degree of this vertex and 1 to the degree of this vertex. So the total degree should be twice the number of edges. So this is 2m squared. And so what does Cauchy-Schwarz say? Well, Cauchy-Schwarz says that the sum, if I have some variables, ui and vi, then this inequality holds. And so with this d of x squared, it kind of looks like this. I'm just missing a second variable. I can just make that 1. So there's like a little 1 there. So then this is less than or equal to the sum of 1 squared times the sum of d of x squared. And the sum of 1 squared is, well, we're summing over the number of vertices, right? This is like x and v of g. This is x and v of g. And there's n of them. So this is just equal to n times the sum of d of x squared. But d of x squared is less than or equal to mn. So this is less than or equal to mn squared. And now, if we combine everything, or we just look at the endpoints of the inequality, we have 4m squared is less than or equal to mn squared. So we cancel out the m's, and then we get that the number of edges is at most n squared over 4. And we're done.